in Lesson 9.4, we're talking about direct variation, and you will be able to identify direct variation and also use direct variation to solve problems. We did talk about direct variation earlier in the year, but it makes sense to bring it up again in Chapter 9 when we're talking about linear equations, because direct variation graphs will be a straight line, but there will be another component to look for. So we have two vocabulary words, direct variation and constant variation, and the key concept here, make sure you make note of this. A direct variation is a relationship which the ratio of y to x is constant. So when we take the y value divided by x, we're going to be getting the same number each time, no matter what values we pick for x and y. So 0, 0, 1, 2, okay, no matter what point we pick on the line, that is going to be a constant. And then also, another way to say that is we say that y varies directly with x, okay? And when we take y divided by x, we get what's called the slope, the m, or y equals mx, okay? And if m right here was 0, then we would not have a direct variation because m cannot equal 0, because we know that anything times 0 is going to be 0, and then we'll have something like this: y equals 0 times x, which is y equals 0. And that is a linear equation. It's still going to make a horizontal line at the number 0, but it's not going to have that component where the y value is varying directly with x. Okay, and here's an example: y equals 2x. At the bottom of page 405, you'll get the definitions for direct variation and constant of variation. Okay, the part to note here is that since 0, 0 is a solution to that equation, the graph of a direct variation always passes through the origin. Okay, so that's one way you can check right away if you have a graph and you can see if 0, 0 is a solution. It doesn't mean that if it doesn't pass through the origin that it's not a linear equation, because we can still have lots of different lines that pass through different points on the y-axis. It's just that if it passes through 0, 0, that has to be true for it to be a direct variation. Okay, and then we call that m value, that slope. Okay, we have lots of different words here to keep straight, but the m, the slope, is called the constant of variation, and it actually has another identity or another name for it, and it's called k. So as we go through these lessons, hopefully you're picking up that there's lots of different ways to refer to things, but it still means the same thing. Earlier we talked about y equals f of x. F of x is just function notations. It's another way to say y. And in this same situation, here we have y equals mx, where m is the slope. It's also referred to as the constant of variation when we're talking about direct variation, and it also has the letter k. Okay? All right, so at the top of page 406, we're looking at example 1. Notice if you are given a graph to refer to, it makes it pretty easy to identify whether or not it's a direct variation. First off, 0, 0 is a point, so that's good. And then we want to make sure that we are getting the same constant when we take the y divided by x. And so in this case, we're taking 14 divided by 4, and we get 350. And then we take another 28 divided by 8, which is 350. Okay, up 2 over 2, up 2 over 2. It's constantly rising at the same rate. So you can do that mathematically by showing the y increase over the x increase and the y increase over the x increase. Notice that each time it's consistently increasing 350. Okay, up 350 is the constant rate. Okay, and again, since it passes through the origin, we are going to say that the cost varies directly with the weight. The cost, the y, varies directly with the x, the weight. Okay, let's take a look at number 1. Tyler charging his customers $10 a week plus $5 every time he walks their dog. So determine whether that is a constant variation. Okay, so let's just make a quick t-table here, and let's put down one time that they walk the dog. Okay, and so that would be $10 for the week plus the $5 that he walked the dog that one time. So that's going to be $15. Let's say that he walked the dog twice in a week. Twice would be $10 for $5 each time he walks the dog plus another 10, which is $20. Okay, let's say he walked the dog 0 times. Well, if he didn't walk the dog at all, he's still going to get charged that $10. And this is going to be our point to pay attention to, because if we graph this, okay, 0, 10 is going to be right here, and then 2, 20 somewhere here. It does not pass through the origins. Determine whether the relationship between the total weekly cost and the number of times he walks the dog is a constant variation. In the example here, no, the ratio, the number of walks divided by the pay, is different for every pair of values. And so, for instance, if we took 15 divided by 1, we get 15. If we get 20 divided by 2, that's 10. These numbers here, when we divide that, is not the same, so we're not going to say it's a constant variation, and we're not going to say it's a direct variation because it doesn't pass through the origin. On example number 2, it says the equation y equals 40x represents the distance in miles an ostrich can travel in x hours. Determine whether there is a constant of variation. If so, explain what it represents. Okay, so y equals mx, y equals 40x. 40 is that constant of variation, and we can say that 40 is equal to y over x. All they did there is divide by x on each side. So divide by x, y over x equals 40. So the constant of variation is 40, and that just means that an ostrich can travel 40 miles per hour. For example number 2, the equation P equals 6s relates the perimeter of a hexagon to the length of a side, and determine whether or not that's a constant of variation. If there's a constant of variation, if so, explain what it means. Okay, because we can write that as 6 equals P over S, then the constant of variation is going to be 6, and what that means is that the perimeter of the hexagon varies directly with the length of a side. Okay, depending on the side length, the perimeter is going to vary directly with that by a constant of 6 because there's 6 sides on a hexagon. In 2b, the equation K equals C plus 213, and that relates the Kelvin temperature to Celsius temperature, and determine whether or not there's a constant of variation. Okay, the key thing to keep in mind here is that if it's a direct variation, it's going to look something like this: y equals mx or y equals kx, where there's no, well, 0 is the y-intercept, okay, and then there is that constant. The coefficient is going to be our constant, okay, and this equation right here does not fit into that format. Okay, so there is no constant of variation. Kelvin temperature does not vary directly with Celsius. Okay, so 0, 0, if I plugged in 0 for Kelvin, or K equals Celsius 0 plus 273, we see that 0, 0 is not a solution, which means that it's not a direct variation, and there's not a constant of variation there. So a couple things to keep in mind. It's going to look differently in different situations, and you need to be aware of that. For example 3, at the top of page 407, we have a nice graph for us here, and again we can see that it crosses the point 0, 0, so it is going to give us that information about being a direct variation when it passes through 0, 0. Okay, and then we have some different points on the graph, and of course if those points fall on an exact coordinate there, it's easy to tell that 40 divided by 10 is 4, and 100 divided by 25 is 4. So it's looking like the constant of variation is 4. But in this case, it just says use the equation y equals mx. Choose any point on the graph. Okay, so they chose the point 2.510. Okay, and then they divided 10 divided by 2.5, and they got 4. Okay, and then you can see that that doesn't matter what point you would have picked. 15 divided by 3.75 is also 4. So 4 is our constant, and the way we write that is y equals 4x. For the final step, it says write the direct variation equation and replace x with 700 because it asked in the question how long will it take to fill a 700 megabyte CD. So we're going to substitute in the 700 for x, multiply that by the 4, and it will take 2800 seconds. For 3, the cost of bulk peanuts varies directly. So when it varies directly, we know that it's going to cross 0, 0. Obviously, if you purchase 0 peanuts, it's going to cost $0. So 0, 0 is a solution. Okay, and then we also know that it increases at a constant rate or decreases at a constant rate. In this case, at a local store, 2 pounds of peanuts cost $5.80. Okay, so we should be able to take $5.80 divided by 2, and we can get the cost of each pound to be 2.9. So the way we write that in our equation is y equals 2.9 times the number of pounds of peanuts. And then it says find out how much 5 pounds costs. So all we're going to do is substitute that 5 in for x, and we get that 5 pounds is going to cost $14.50. The equation y equals 1.5x represents the relationship between the number of heartbeats and the time in seconds. The graph shows the heartbeats for a cat. Which animal has a faster heart rate? Okay, so we have y equals 1.5x for the dog, and then we have y equals something for a cat. Okay, so let's take a look here. 2 divided by 1 is 2. 4 divided by 2 is 2, 8 divided by 4 is 2, and 6 divided by 3 is 2. So the constant of variation there is 2, so 2x. And so 2 is faster than 1.5, so the cat has the faster heart rate. Let's take a look at number 4 here. Y equals 3x is the heart rate of a rabbit, and which one has a faster heartbeat, the rabbit or the cat? Well, we said the cat's was 2 and the rabbit was 3. So since the rabbit is 3 beats per second, okay, that's going to be greater than 2 beats per second for the cat. In lesson 9.5, we learn about a specific type of linear equation written in a specific form called slope-intercept form. And in slope-intercept form, we have what's called the slope and y-intercept of a linear equation. So you're going to be able to determine that if you see an equation written in slope-intercept form, and then you're going to graph it using this form. Okay, still going to make a line just like direct variation made a line. Okay, but this is a specific format that when you see it in this format, there's kind of a little trick there. Not trick, but just a shortcut. One vocabulary word, slope-intercept form. Slope-intercept form looks like this. Y equals mx plus b, where m is the slope and b is the y-intercept. And if you remember from last section in direct variation, it looks like this. Y equals mx. There is no y-intercept, meaning that it crosses at 0. This equation right here is not a direct variation because it does not cross the origin 0, 0, but it's still linear. It makes a line, and there is a slope, m, that we are going to be able to identify. So at the bottom of page 412, it says state the slope and the y-intercept. Well, if it's written in this really handy-dandy format, it's super easy to identify the slope and the y-intercept. The slope, it's what's in front of the x, called the coefficient of x, right? And so in A, 1a, 3 is the slope. And the y-intercept is always that plus or minus afterwards. In this case, the y-intercept is 1. And in this case, the slope is what's in front of x, the coefficient, -2, and what's after is nothing. So it's a y-intercept of 0. Pretty easy to identify if it's written in that format. So what? What does that help me with? Well, before we get to how that's going to help, let's just look at this equation right here at the top of page 413 that's not written in slope-intercept form. It can easily be put into slope-intercept form by adding 4x to each side. When you add 4x, you get y equals 2 plus 4x, and since the commutative property says we can switch around the order and not change, we can put that as y equals 4x plus 2, which is in the format y equals mx plus b. So 4 is our m and b is our 2. So let's take a look at these right here. Since y is by itself there, we can take away 6x, take away 6x, and we get y equals -6x minus 3. So our slope is -6, our y-intercept is -3. If I add 5x, I get y equals 5x plus 10. So my y-intercept is 5. I just said that wrong. My slope is 5, my y-intercept is 10. Okay? On this one right here, I'm going to add 5, and get y equals -x plus 5. The coefficient of the x is a -1 for my slope, and my y-intercept is 5. And lastly, if I take away 2, I get y equals x minus 2, or if you had it -2 plus x, that's fine. But slope-intercept form is always written y equals mx plus b, so that x does come first there. So the slope is 1, and then our y-intercept is -2. So again, getting back to how is this going to help us? So what? Well, it's going to be pretty easy to graph equations in slope-intercept form because what you do is you find the y-intercept, which is 3 in this case, so you just count up 3 on the y-axis and put a dot there. And then you use the slope, -2/3, to get another point. You can either go down 2 to the right 3, or you could go up 2 and to the left 3. Okay, and when you graph that, you get a line, not a direct variation because it doesn't pass through the origin, but it's still a line. And it makes it really slick to graph these without making a t-table. So let's take a look at number 3 at the bottom here, y equals -x minus 2. What you do is you start by doing that y-intercept, which is -2. So we go down 1, 2. Should make that a straighter line there. Sorry about that. That probably just made it worse. But -2, and then our slope is -1. And so sometimes it helps to write that slope as a fraction. So I'm going to write down -1 over 1. So from this first point, this y-intercept, I'm going to go down 1. That's a -1. And I'm going to go to the right 1 and put a dot. I could go up 1, but then I'd have to go to the left 1 for that negative number. Okay, because -1 over 1 is the same thing as 1 over -1. And you have to pay attention when you're graphing. Going down is going to be a negative, and going left is going to be a negative. So when you're graphing, just pay attention to that, and we'll get lots of practice this chapter with graphing. Okay, so that's what number 3 looks like. For the next one, the example at top of page 414, a typical leopard gecko is 3 inches long at birth. So that's where you see the first point on our graph. At birth, 0 years, it's 3 inches long. And then it increases a 1/3 of an inch per week. So that's where you get that slope, or how much it excuse me, increases. Excuse me. So we plotted the 0, 3, and then we go up 1 over 3 and put a dot. up 1 over 3 and put a dot. In this case, it wouldn't make sense to go down 1 to the left 3 because then that would say that the gecko is negative 3 years old. So in this case, that negative, the other movement doesn't make sense. But just know that you can do it in the other direction if it makes sense to do that. So the y-intercept 3 represents the length at birth, and then the 1/3 represents the growth rate in inches per week. Let's take a look at 4. Jack has written 30 pages of his novel, and he plans to write 12 pages per week until it's completed. So it's starting at 30, that's where the plus 30 comes from, and then 12 per week until it's finished. So to graph that, okay, we can count by 5s, 5, 10, 15, 20, 25, 30. Right now we're starting at 30. Okay, now he's going to want to write 12 pages per week. So here's week 1, here's week 2, here's week 3, here's week 4, etc. Okay, so if we use that 12 over 1, this is where it gets kind of tricky if you don't have graph paper, because from this point we're going to go up 12 over 1. And then we're going to go up 12 over 1. And you can't tell that exactly that I'm going up 12 because I don't have graph paper and it's not labeled very nicely. But we're just going to connect those. Okay, and really this part doesn't matter because this is where we're starting at. Describe what the y-intercept means. The y-intercept means that he started at 30 pages already being finished. Okay, and the slope represents how much he's going to write per week until it's finished. Okay, hopefully that helps you. We're going to do a lot more practice with graphing in slope-intercept form and actually in other formats. So make sure to request a Google Hangout if you have a question or email. Let me know how I can help.